Welcome, ladies and gentlemen, here to the technical forum of the group exhibit Hydrogen Fuel Cells and Batteries. We are looking forward to the next presentation, which will be very interesting for you, for most of you, because it's very interesting from PneumatiCoat Technologies from Colorado, United States. And Dr. Paul Lichty, the CEO of PneumatiCoat, will talk about high-volume ALD coating of lithium-ion materials, improve safety and versatility. I'm looking forward to that.
All right, thank you.
Hello, Paul.
All right, well, thanks everybody for allowing us this opportunity to speak. After walking around a little bit, I realized we should have done a fuel cell-based presentation, but if I can convey accurately what it is we do from a scientific standpoint and a manufacturing standpoint, then that'll be the most powerful thing I can provide in terms of information for you going forward with the products that you're interested in producing. What we do is basically we take powders, we do a very conformal, uniform coating process using something called ALD as the production method, and we can tailor or nano-engineer the surfaces of these powders in order to provide all kinds of benefits. And that's really the key there, is we can decide what benefits we want, what benefits we don't want, and tailor custom products for you. So this is probably the most important slide, and if I do a good job explaining what we do, then the light bulb will go off on your head and you can take this back to whatever products you're manufacturing and understand kind of the power of this coating process, and now that it's scalable, the ability to incorporate that in whatever products you're making. So ALD, or atomic layer deposition, is a gas phase process. So what that means is we can do things like powder, we can do porous objects, we can do all kinds of things that previously were unable to be coated or unable to be coated uniformly because you have line of sight issues, whether you're using some sort of ion deposition. Now the other aspect is the fact that it's self-limiting, which means we take these gases, they bond to the surface of whatever your particle is, and then they shut off. And so we pull out the excess, we add the next precursor, and then we start building these layers literally one molecule at a time. And we can do that on billions of particles at any one time in order to develop a surface that can be sub-nanometer, angstrom level, or build it up to several nanometers, or tens or hundreds of nanometers. So you can really have an extreme amount of control with this. We can do all kinds of substrates or materials that weren't previously capable, and the uniformity of the coating is again the key. Each monolayer is pinhole free, extremely uniform, and that allows you to get by with much thinner coatings compared to something like a sol gel or a CVD type coating process, where you're going to have variability in the performance based on the thickness and the conformality. So the other aspects of ALD that are very interesting, and probably more so in fuel cells, is the ability to do multi-layers for incorporating, and this is the nano-engineering part, incorporating all kinds of different corrosion resistance, catalytic activity, dispersion improvements, whatever you're looking for. And then using this process, you can also fine-tune catalysts. When you do ALD of metals, you can basically tune the size of the islands down to 1 nanometer, 2 nanometer, 3 nanometer. You can control that, and then you can also protect it. So if you're looking for reduction in coking or higher activity for some non-precious metals, those are the kind of things, that's the 10-second or the nickel overview of why ALD is important and powerful for a whole host of applications. So in terms of particle ALD, it was actually invented in 1992, so it's been around for a while, but it's all been in universities, national labs, small-scale production methods, which a lot of technologies that are very powerful and very interesting stay at that level for a very long time, and they don't come out into commercial products because there's not a manufacturing technology. And so it's the ability to manufacture these things at large scale that is the other key important thing. And that's something that PneumatiCoat has been focused on, is not just the technology, not just the applications, but really the scale up of that transformative technology. So this is this is the difference between what's previously been done, small scale fluidized bed systems for particles. You have to keep them separated so you're not gluing them together, where you're doing tens or maybe hundreds of grams. I think the best case is maybe a couple kilos a day for coating process, to what our high throughput technology is, which is capable of hundreds of kilos today. And what that does is it brings down the capital cost and the labor pricing to a level where it's actually meaningful for the products you're looking at. On our production roadmap, we're already at the stage where we're able to produce hundreds of kilograms per day. This year, we're going to finish completion on our next line of pilot plant that's going to be able to do thousands of kilos per day. And each time you scale, you benefit from those economies of scale, and you see a big reduction in the price to levels that are meaningful in industry, where $1 a kilo additive process actually is going to be cheaper because of the performance improvements. And I'll go into that example for batteries, and then you can take that with you for fuel cells, catalysts, whatever products you're producing. For lithium-ion batteries, when we do these really thin coatings, and these are sub-nanometer coatings on, most of the data is going to be cathode materials. We also do anode materials. The benefits you get, it's better to think of it as kind of a protective energy barrier rather than an actual physical coating, because it's so small. It still allows conduction of ions, but it prevents a lot of the bad side reactions that occur when you're cycling batteries. So it allows you to take that material and then cycle it at much faster C rates, take a standard material and move it up to higher voltage operations, so the capacity of your normal NMC can be increased 15-20% without changing anything else in the battery. It also improves the high temperature performance, so that if you have a real world battery application and you have a vehicle or something that sees a hot day, you're not degrading the battery because it sees a summer's worth of hot days. It actually maintains its cycle lifetime, and that's the other improvement. You can abuse these materials a lot more and maintain a longer cycle life, which is kind of the watershed. A lot of these combined create a watershed for applications of lithium-ion batteries in grid, in vehicle, in consumer electronics. These are all things that push us into a direction where we can create much more market adoption. The other improvements are actually safety. By restricting the growth of an SEI, you reduce the impedance buildup, which is what causes heat generation. So your batteries are going to run cooler longer, and we shift the exothermic reaction temperature between the cathode and the electrolyte material, so that if you get 30 degrees of increased temperature before you have a runaway reaction, or what we've all seen with some of these fires in batteries, 30 degrees may not sound like a lot, but when you have an active battery management system, you're talking about a rate problem rather than just a specific temperature problem, and that actually gives you a huge amount of leeway in terms of safety and the temperatures you can get to, and the requirements for the battery management system to keep your whole battery safe. And the final one is cost, which may be counterintuitive because we're adding a process to your production step. But with all of these benefits, it allows you to use less material for the battery or use those batteries longer. So either your dollar per kilowatt hour, depending on if you want higher energy density or higher lifetime, your dollar per kilowatt hour or your dollar per kilowatt hour per cycle cost goes down because you don't need to plan on contingencies or have an increased safety factor for your production of the battery. And just to give you an example, this isn't a very appealing looking table, but it goes through some of what we've done, some of what our partners have done, some of what's been in literature, and just gives you a good idea that this is material agnostic. We've coated all kinds of anode materials and cathode materials, and in each instance, once you nano engineer the correct surface, you can get a pretty large benefit at some of these really harsh conditions. These voltages are not normal for these materials. These temperatures in the high temperature cases are not normal, and they usually kill the materials. And that's what this nano-engineered surface that's going to be less than a couple nanometers can enable. Right now, where we're at with specifically lithium-ion is we're working with a number of companies, over 30 development partners, and we've tested cells all the way up to 40 amp hours, and we're looking at building some beyond that. So this isn't coin cell data. This is actually large scale. We're seeing these benefits beyond kind of that typical question mark when you're in a coin cell and there's too much variability. We've compared this to other coating methods, conventional sol gel, CVD type coated materials. They do provide a benefit to some of the baseline, but because of the uniformity, we tend to see a lot better improvement. We've compared it to ALD on the cast electrodes, which again, in a production process, we think the powder coating is a little bit simpler. It's drop-in ready, rather than putting a coating system in between a roll-to-roll type of process. But the particles still perform better. So this is very much a manufacturing capable process that is easy to drop in because we're not dramatically changing the cells or anything that you're doing. You can start with a dry powder. We give you a dry powder, and your process continues on in the same way. So that's part of the manufacturability and the integration that's, I think, is key when we're talking about real-world implementation of new technology. So I talked a lot about batteries, and if you understand what it is that we do or how powerful the coating technique is, things we can do for fuel cells involve protecting some of the cathode materials from, in SOFCs, protecting them from degradation over time. We can coat some of the catalytic materials in membranes in order to either protect those or add higher catalytic activity, all at lower loadings because we can custom engineer the catalyst and the particle size to be both more active and less weight percent. And that comes into play with catalysts. Some of these other applications, we're talking about oxidation-resistant metals, bumping up the oxidation temperature of a metal by as much as 100, 150 degrees, while maintaining electrical conductivity. So that's pretty powerful. And this is just an example of kind of all the things that we did, but if I did a good job explaining to you kind of what ALD does, the manufacturability, please come talk to me or come see us at our booth. That's just over to the right, and I'd be happy to answer any questions you have.
Thank you very much for this presentation. Thank you very much. Here's your applause. So are there any questions so far? So please raise your hand. I'll be with the microphone right with you. Not at the moment, or maybe you're too shy, I don't know.
I must have done a really good job explaining things.
So whenever you have a question, the booth is just right over there. You can see, right, beat 32-1, where the hand is up over there. Or do you have a question? No, you don't have a question. Okay, very good. So once again, Paul, thank you very much for the wonderful presentation. Here's your applause.
Thank you very much.
Thank you, Paul. So just stay tuned. Just in a few minutes' time, we have the next presentation here in our technical forum from Dr. Eva Raun-Nielsen. She is Center Manager of DTU Energy FCH Test Center from Roskilde in Denmark, and she will talk about the European fuel cell and electrolyzers activities, testing, test procedures, and demonstration projects. We will start in 6 minutes' time. Thank you.